Hello everyone, and today we're going to talk about rendering in our game engine. And first thing that we're going to talk about is cross-platform rendering. What is a cross-platform rendering? Suppose we have some renderer, and you have some draw method in your renderer. And when you are on Windows, like when you call your draw method, your renderer actually knows that you are, for example, on Windows. And if you're on Windows, it will call some draw method, some Windows draw method. And if you are on Linux, then it will call some Linux draw method. So that's actually the basic idea of cross-platform application in any kind of cross-platform application. But if we will talk especially about our renderer, then it will be a little bit differently, because this is actually your API, or in other words, abstraction layer. And this is your implementation. But in this case, our implementation is like per operation system. And in case of rendering, it's not exactly like this, because we will rather say that our implementation is per graphics API. I mean, per DirectX, per Vulkan, per OpenGL, and stuff like that. And we can use different graphics API per one operation system. For example, in Windows, we can use like DirectX, we can use Vulkan, we can use OpenGL, and so forth. So yeah, that's kind of a basic idea. We will have some API, our API, and we will have implementation for this API. And then using this API, we will create some kind of render 2D and render 3D stuffs. Because honestly, this API is just something simple. I mean, like create me resource, create me texture, create me shader, create me buffer, bind me this buffer, bind me this shader, draw something. So it's like low level stuff for our renderer. It's not something like draw me a rectangle with this color at this position with this size. So it's not like that. It's not that high level. So in order to have like drawing some rectangle and stuff like that, we need to have some render 2D class. So that's gonna be our renderer 2D class. So what this class will actually do? Firstly, we want to draw some primitives. We will start with rectangles because it's like the simplest one maybe. So we want to draw rectangle, and it's not only the simplest one, but if you will think about it, every sprite that you have in 2D games, it's a rectangle. So yeah, that's why rectangle is the first choice. So rectangle can be colored. For example, I don't know, maybe we want to have some pink rectangle, yeah, with this size, this kind of position, and maybe rotation also. Also, we want to have some maybe textured rectangle, yeah. You definitely want to have them because it's just a sprite. So it's like a texture here. Also, what we want to have is maybe kind of another primitives like a circle. So our render 2D will actually be able to draw not just triangle. We can add some circles, maybe not rectangle, excuse me. We can also draw some triangle. What else? I don't know. And maybe some user-defined primitives, because if user wants something like this, for example, this is a primitive, and maybe it also wants to not just to use some texture for this primitive or to use some color for this primitive, maybe it also wants to use his shader for this primitive in order to determine each pixel color of this primitive. So that's kind of stuff that you need to handle with all the primitive. Also, talking about primitive, maybe we want to have some lines, because lines is actually even useful in 3D rendering. You can outline some models using 2D renderer for debug stuff. Maybe in 2D we also can use some lines for debug like collision or something like that. So also we need to have a text render in our game. In any kind of game, we will have text. So we need to draw text. Also, I want to talk about some CPU particle system, but we will also will talk about it in more detail. We'll talk about what is a CPU particle system, what is a GPU particle system. But just for now, we want to have some particle. Particle is just, for example, some fire effect. So there is a lot of particles. They are like transparent a little bit and stuff like that, and they just form a fire effect or something like that. Or just a smoke. Also, this is not like technical requirements. This is just like features that we want to support. But we also want to talk about technical requirements. And first things that I would like to talk about is how we will draw these primitives. I mean, if our user will call like draw rectangle, do you want to just draw this rectangle immediately to the screen? I mean, that's your screen and you want to draw, for example, like 3 rectangle, yeah, or like 10 rectangle, whatever. If you want to draw them one by one, I mean, if you call draw 3 times, then it will be not that beautiful, not that right. Oh, excuse me, this is too huge. Anyway, it will not be that good to draw them one by one and draw them immediately. It will be better to store some information about this draw and about this draw to some buffer and then just draw the entire buffer. I mean, what we need to do, what we need to have in order to draw this like rectangle, we need to have like 4 vertices information. So it's like 4 vertices information for this draw call and 4 vertices information for that draw call. And that's it. And then we draw this buffer entirely. And if you will draw like 10 rectangles, you will not notice any differences because it's just 10 rectangles. But if you will draw like 100 or maybe like 1,000, 10,000, I don't know, then you will definitely notice the difference between this in case of performance, because you will actually see the exactly the same picture, but the performance will be really different. And this process of like taking the data for each draw call to some buffer and then just flush the entire buffer is called a batch rendering. We will also talk about instance rendering when we will implement this, because instance rendering is just pretty much the same stuff as this, but we will also have an ability to specify some instance data. For example, you can notice that I don't talk about color here because we also have some color for this like rectangles. Then when we will have this color, so the color can be specified in our instance buffer. So the color is 16 bytes, which is like 4 floats, and we can say that, for example, we have like 4 vertices, yeah, so that's our instance buffer and that's our vertices buffer. So we will have like 1, 2, 3, and 4 vertices per one instance, yeah. So that's our instance and that's 4 vertices. And we specify that our instance has 4 vertices and this is our instance data. So for this 4 vertices, we will use just this one color. We will not use like 4 different colors for each vertices and then interpolate or use no interpolation in shaders. So maybe I talk a little bit about technical implementation of this, and I don't want to do this currently, but anyway, so hope you understand all of this stuff, and we will talk about this later. Also about 3D rendering. We actually finished with 2D renderings. That's everything that I would like to talk about. All of these primitives, line text, and instance drawing. Okay, so what about 3D rendering? Is it that simple as just creating like a render 3D class? No, not really. Because there is a lot of systems in 3D rendering. I mean, you will have the basic system is just a material system and shader system. So what is this? For example, you have some model. Yeah, your model is just I don't know, maybe a cube. And how do you want to render this cube? Like what kind of material it will actually have? So what is actually a material? A material is just a data. I mean, you can have some like colored material, which is just some RGBA color. So and you can actually apply this material instance to this object. And then if this is like a pink, then this cube will be shaded like just a pink cube without any lighting and stuff like that. So it just will be a pink cube. But if you want to have, for example, another type of material, you will have physically based rendering material, for example. This is just a material that will draw your cube as physically correct as it possible. So if you will assign this PBR material, then your cube will be rendered differently. What I mean by saying will be rendered differently is that your renderer is just a place which determines how your models will be rendered. I mean, it takes the material type and it just determine some shader, or even not just shader, but the entire rendering path, like how you will render this object. And if this is, for example, just a colored material applied for this cube, then it will be really simple. You just will have in pixel shader just return the color, and that's gonna be really simple. In PBR, you will also take into consideration all the light there is in the scene. You will calculate like light impact for all the lights and stuff like that. Also about some kind of technical requirements, because this is just our how all this will work, and there is like optimizational stuff for 3D rendering, because yeah, it will be really complicated. And the first thing is multi-threading rendering, because in 2D rendering, I don't talk about multi-threading at all. Why? Because multi-threading in 2D renderer is it's not that good. I mean, it will not give you anything, because rendering a 2D scene is not that complicated. It will not take too much time. So you can actually render everything in one thread. But in 3D, you couldn't do this. You should have rendering on second thread, or like use some multi-threading rendering. And the basic architecture with this is that you will have your main thread. Yeah, suppose this is just 2D renderer. Yeah, you have some code in it, and some code is a render code. So it's like a draw. Yeah, so draw our rectangle, and for simplicity, it will immediately draw them. Yeah, but in your architecture of 3D rendering, you will also have some another thread for just for rendering, and you will ask me like how can I see this like draw call from my main thread and then just execute this on the rendering thread? So you can definitely just have some command list for your main thread and push all the rendering command to this list. So you will have this kind of list with all the commands that you want to execute, you want to render. And then at the end of a frame, you will synchronize, because rendering thread will also have some command lists that it will process. So if there is some commands still in this rendering thread, then it will execute this command. If there is nothing, like if it's empty, then our rendering thread is done, and we can actually from main thread at the end of a frame, we can take some values whether rendering thread is done or not. And if it is, then what we do, we copy this command list to this one, or we just swap them technically, and then we can use our empty command list again in our main thread, and we can use this not empty command list in order to read from them from the rendering thread. But in this kind of architecture, your main thread will render the second frame, for example, but your rendering thread will render the first one. So your rendering thread will always be one frame behind your main thread. That's not a huge issue because we will have all the resources will be like a shared pointer, so there will be no cases like main thread is done, but render thread like using some resources that are currently deleted. So it's not that huge issue, but it will actually give us a huge performance in ideal case when you have like 16.6 milliseconds, which is 60 FPS for the entire frame. Um, Ideally, if this takes 50% and this takes 50%, your frame rate from single thread to two threads will become 8.3 milliseconds. So that's kind of beautiful. It's really good for performance. Also, what I would like to talk about is lighting. So that's the last thing that I would like to talk today. As I said, in PBR, in any other kind of stuff, we use lighting, yeah? So that's another optimization because in games, there is a lot of lights. And how to calculate impact of the lights to our model. So we go through each light in our scene. We will have some container of lights, and we go through each light, and we just calculate the impact of this light for this pixel. So we calculate how far from the light this pixel is, what is the intensity of the light. So there's like different parameters, but the thing is that we calculate this for each light. We go through each light and calculate this. But most of the lights, they will not affect on our pixel. For example, if you have some open world scene, there is a really small amount of light that affect your pixel. I mean, a directional light, maybe your character just holds some lights. So there is like two lights that affect most of the pixel in your scene. But you can have like 100 lights. So you will just calculate lights impact for 98 lights that will not affect your pixel at all. So for this, we use like, there is two technologies of rendering. There is like forward plus rendering. So this rendering, when we go through each slide, it names forward rendering, but we can use something like forward plus rendering. It will still go through each slide, but it will calculate in compute shader, not in pixel shader. It will compute the actual effect area of the slide. I mean, it will compute that, for example, this slide has this area of a scene, yeah? So for example, this slide is here and it takes this area. It has some effect to this area, to these pixels, yeah? But this, for example, has this effect area. And then there is some other lights that are far away from what we currently see, and the effect area doesn't really um, how that we actually doesn't see any pixels that is inside of this effect area. So that's kind of an issue. And we calculate all these areas, and then when we draw, we take the pixel, and for each pixel we will calculate what kind of light actually affect on this specific pixel. And we're gonna calculate light impact only for these lights because we know that they actually have some effect to this pixel. And that's kind of improvements for performance. So that's a forward plus rendering. The third rendering is a little bit complicated because what is a deferred rendering? And it's not like real rendering as most programmers said, because in deferred rendering, you render to each textures, which forms a G buffer. I don't want to talk about this really because that's a little bit complicated for now. But anyway, you draw two textures. So for example, you can draw your scene just to normal texture. So you have, for example, this in your screen, yeah? And you draw your scene just with normal. So for each pixel, you calculate only a normal of this pixel in your scene. Then, for example, for like, I don't know, what we can also have a world position buffer, yeah? So that's textures, they name their buffers. Because they form a G buffer. So the G buffer is just a collection of these textures. And then when we draw all of this, we can draw them using separate render threads. But anyway, we can do whatever we want. So this is just a one thread, this is another thread, and maybe third thread for, I don't know, color or something like that. So yeah. And then when we draw all of them, we go to something called a lighting path. A lighting path is just something that calculates the lighting effect. So we can have also here, we can draw some light areas buffer. I mean, this will determine how each light, honestly, it will be similar to this. So we will, oh, excuse me, we will see something like this, but we will see this on another buffer. It will be faster technically, not that much faster, but anyway, it will be faster. But it also a little bit complicated architecture, and yeah, it will be complicated. Maybe we will not use this, but we will definitely fastly use forward plus rendering. It's not that bad. I mean, we can draw lots of light, more than enough for our games, because we will not create some 3D renderer like in Unreal. It can look like this, but technically it will not be even close to it. So yeah, that's kind of everything I would like to talk about today. And don't forget to subscribe on this channel, hit the like button, wrote some comments about all of this stuff. Maybe you don't understand something, I will explain to you in much more details in comments. So yeah, goodbye, see you next time.